In this video, we will explain how to compute the determinant of a matrix n by n. Before doing that, we need to explain several notions. Let's start with the notion of a submatrix A, I, J. And by this, I mean an n minus 1 times n minus 1 matrix. And it's the matrix that we get when we remove the ith row and the jth column. Let's do an example. If we have this matrix 2, 3, 1, 4, 0, negative 1, 4, 3, 2, 1, 4, 7, and negative 1, 1, 2, 17. Then if I want to compute the matrix A, 2, 3, that means that I have to remove the second row and the third column. Then I end up with the matrix 2, 3, 4, because this column has been removed, this row has been removed, and then I have 2, 1, 7, and negative 1, 1, 17. This is A23, this is submatrix A23. For example, the submatrix A14. That means that I have to remove the first row and the fourth column. Then in this case, I will get this submatrix. 0, negative 1, 4, 2, 1, 4, negative 1, 1, 2. And then we have n squared submatrices that can be defined for a given n by n matrix. We're going to define a minor ij, and this is just going to be the determinant of the submatrix A, I, J. And we're going to define the cofactor ij to be equal to negative 1 to the I plus j times the minor ij. That means that this is negative 1 to the I plus j times the determinant of the matrix A, I, J. Let's do some example here. The minor for this matrix, the minor 2, 3 would be equal to the determinant of this matrix 2, 3, 4, 2, 1, 7, negative 1, 1, 17. Notice that there is a way to compute this determinant. And the cofactor 2, 3 is going to be equal to negative 1 to the 2 plus 3 times the determinant of this matrix. But this negative 1 to the 2 plus 3 is going to be minus 1 times the determinant of the matrix A, 2, 3. Then, once we have defined the notion of cofactor, then we can define the notion of the determinant of any n by n matrix. Somehow, this definition is by induction because we know how to define the determinant of a 2 by 2. We know how to define the determinant of a 3 by 3. But then, in general, we're going to define the determinant of a n by n matrix in terms of determinants of n minus 1 times n minus 1 matrices. Let's do the definition. definition. The determinant of A, let me just say, using the Laplace expansion about row I is equal to AI1 cofactor I1 plus AI2 cofactor I2 plus AIN cofactor IN. Essentially, here is the ith row, and then what we do is we take this number and then we multiply it by the determinant of the matrix that we get by removing this row and this column, and then we multiply by the number -1 to the I plus 1, and then we keep going like this. Let's do an example. Let's suppose that we have the matrix 3, 2, 1, 0, 1, -1, 3, 4, 7. Then if I want to use the third row, then I have to compute three cofactors. I have to compute the cofactor 3, 1. I have to compute the cofactor 3, 2, and the cofactor 3, 3. But then the cofactor 3, 1 by definition is -1 to the 3 plus 1, which is just 1, times the determinant of the matrix 3, 1. That means that I to the matrix A 3, 1. Let's suppose that this is the matrix A, and then we get that this is equal to just the determinant of the matrix 2, 1, 1, -1. And this is just -2, -2 minus 1, -3. Then this cofactor is -3. To compute this cofactor, I need to do -1 to the 3 plus 2. This is the position 3, 2. And then times the determinant of the submatrix A 3, 2. But this submatrix 3 plus 2, and this is the determinant. The matrix, when I remove the third column and the second row, I get 3, 0, 1, -1. And this is equal to -1 times, and this determinant is -3. That means that this is 3. This cofactor is +3. Finally, this cofactor is just -1 to the 3 plus 3 times the determinant of the matrix that I get by removing the third column and the third row, then the matrix 3, 2, 0, 1, and this is just -1 to the 6 is just +1 times this determinant, which is just 3. Then in this case, this is also 3, and therefore if I use the third row, the determinant of A is going to be 3 times this cofactor plus 4 times this cofactor plus 7 times this cofactor. and then this is negative 9 plus 12 plus 21, which is 24. And maybe after this definition, it's good to know that it doesn't matter what row you pick to do this operation, the answer is going to be the same, and you can actually pick a column if you want as well. And you start with the first element of the column, second, and then so on. Let's see what would be the difficulty of computing a determinant. Let's try to compute a determinant of a 4x4 matrix. Let's take the matrix A equal. Okay, this is a 4x4, and let's suppose that I want to use the third row. Then the cofactor, the determinant of A, is going to be 0 times the cofactor 3, 1 plus 0 times the cofactor 3, 2 plus negative 2 times the cofactor 3, 3 plus 4 times the cofactor 3, 4. And then since this cofactor is multiplied by 0 and this cofactor is multiplied by 0, I'm not going to bother computing those cofactors. Then I have to compute the cofactor 3, 3. Cofactor 3, 3 is going to be equal to negative 1 to the 3 plus 3, which is just 1, times the determinant of the matrix that I get when I remove the third row and the third column. Let's see, I get 1, 0, 0, 0, 1, 2, and here I get, I'm removing also the third row, I'm removing this, then I get 1, negative 1, 1. And to compute this, you need to apply again the formula of the Laplace expansion to compute this determinant. We know that this is like a new problem. How to compute the determinant of this matrix? The determinant of 1, 0, 0, 0, 1, 2, 1, negative 1, 1. Then we can use, for example, the first row. If I use the first row, this is 1 times the cofactor 1, 1, but the cofactor of this matrix, plus 0 times the cofactor 1, 2, plus 0 times the other cofactor, but since it's multiplied by 0, it's just 0. And that means that this is just 1 times the cofactor 1, 1 would be the negative 1 to the 1 plus 1 times the determinant of the matrix that we get when we remove the first row and the first column. We get 1, 2, negative 1, 1. And this is equal to just 1 times 1 is 1 minus negative 2 is 3. Then this determinant is equal to 3. Then what else do I have to compute? This number is just 1 times 3. I need to compute the cofactor 3, 4. And by definition, this is negative 1 to the 3 plus 4 times the determinant of the matrix that we get when we remove the third column and the third row and the fourth column. Then we get 1, 0, negative 1, 0, 1, negative 1, and 1, negative 1, 1. We are removing the third row and the fourth column. 1, 0, negative 1, 0, 1, negative 1, and 1, negative 1, 1. Then to compute this determinant, I need to do to compute this part, I need to use the formula again. And then I can use, for example, the first row. If I use the first row, I will have 1 times the cofactor 1, 1, plus 0 times the cofactor 1, 2, plus negative 1 times the cofactor 1, 3. But what is the cofactor 1, 1? The cofactor 1, 1, by definition, is negative 1 to the 1 plus 1 times the determinant of the matrix that I get when I remove the first row and the first column, 1, negative 1, negative 1, 1, and then plus 0, which I don't, this is going to be 0 anyway, and then plus negative 1 times the cofactor 1, 3. But by definition, the cofactor 1, 3 is negative 1 to the 1 plus 3 times the matrix, the determinant of the matrix that I get when I remove the first row and the third column, 0, 1, 1, negative 1. And therefore, this is just equal to, this determinant here is 1 minus positive 1, this determinant is 0. And this determinant here is negative 1, will be 0 plus negative 1 times 1. 1 plus 3 is 4, negative 1 to the 4 is 1, times this determinant, which is 0 minus 1 is negative 1. Then this determinant is just equal to 1. That means that this is negative 1 to the 7, which is negative 1, times 1, and then I get negative 1. And now that I have these two cofactors, I can keep going, and I can say that the determinant of A is negative 2 times the cofactor 3, 3, but the cofactor 3, 3 is just 3, plus 4 times the cofactor 3, 4, which is negative 1. And then this is equal to negative 6 minus 4, and this is equal to negative 10. Okay, now you can see the difficulty. We know how to compute a determinant of a 4 by 4 matrix because we know how to compute a determinant of a 3 by 3 matrix. But now that we know how to compute a determinant of a 4 by 4, we can compute the determinant of a 5 by 5. Because when you are computing the determinant of a 5 by 5, you will get cofactors. And those cofactors in order to compute those cofactors, you need to compute determinants of 4 by 4. And in order to compute those determinants of a 4 by 4, then you need to compute determinants of 3 by 3, and so on. For that reason, it may be easier to compute the determinant using row reduction. Let's try to do row reduction with this matrix to compute the determinant. When we're going to do row reduction, these are the rules that we need to keep in mind. If we move from matrix A to matrix B by doing a row operation, then if the row operation is this, if you're interchanging two rows, then the determinant of B will be equal to negative the determinant of A. If you do this change, if you add to row I a multiple of another row, then the determinant of B is just equal to the determinant of A. And what about if you multiply a row by alpha? Alpha different from 0. Then the determinant of B would be equal to alpha times the determinant of A. And with this in mind, and also with this property, here we can define what is an upper diagonal matrix. And it is a matrix that may have numbers that they could be 0 in the main diagonal and above the main diagonal. But here below the main diagonal, everything must be 0. This is upper diagonal. Same thing, we can define a lower diagonal. And we can define a diagonal matrix. The lower diagonal matrix will look like this. It will look like numbers in the diagonal and below the diagonal, but above the main diagonal there must be zeros. And a diagonal matrix is just numbers. There are numbers in the main diagonal that could be 0 or different from 0, but everything else you must have zeros. This is a diagonal matrix. And what is important is that the determinant of all these matrices is just the product of the entries in the main diagonal. I'm referring to main diagonal so that you don't get confused with this other diagonal. We usually refer to the diagonal, to this diagonal, to go from the top left to the bottom right. Okay, then with this, we can compute almost every determinant. Let's do this. Let's suppose that we assign this the determinant of A. And then let's do some changes. Let's put a 0 here. Then to do that, we need to change row 4 by adding -1 times row 1. But we know that this change doesn't change the determinant. Then we're going to get a matrix that has the same determinant. And let's see what matrix do I get. I get 1, 0, -1, 0, 0, 1, -1, 2, 0, 0, -2, 4. And here we get this row minus this is 1 minus 1 is 0. -1 minus 0 is -1. 1 minus -1 is 2. 1 minus 0 is 1. And I know that this matrix, the determinant, is the same determinant of A. Now, let's use this one to put a 0 here. Then I'm going to change row 4. I'm going to change row 4 by adding row 2. We know that the matrix that we're going to get, it has the same determinant because this type of change doesn't change the determinant. Then we have that we're going to obtain a matrix with the same determinant. And then here we will get the matrix 1, 0, -1, 0, 0, 1, -1, 2, 0, 0, -2, 4. And here we are adding these two rows. Then we get 0, 0, 1, and here is 3. Now, we can, let's say, if we decide to flip these two rows, if we flip row 3 with row 4, then I get the matrix 1, 0, -1, 0, 0, 1, -1, 2, 0, 0, 1, 3, and 0, 0, -2, 4. But what happened with the determinant when I flip two rows? It changes by a sign. That means that whatever the determinant of this is equal to negative the determinant of A. Then the determinant of this matrix is negative the determinant of A. Let's end by changing the row 4 by adding 2 times row 3. We're going to get this determinant. We're going to get a matrix with the same determinant. Remember, the determinant of this matrix is negative determinant of A. And then this matrix is going to have this determinant. And the matrix that we get is 1, 0, negative 1, 0, 0, 1, negative 1, 2, 0, 0, 1, 3, and 0, 0, we're multiplying by 2 and adding. We get 0, we're multiplying by 2 and adding, we get 10. But then this determinant is easy to compute because this matrix is upper diagonal. You see, it's upper diagonal because below the main diagonal it has zeros. And then what we get is that we get this equation, negative, let me write this equation here. Let's erase this part. We get that negative, the determinant of A is the determinant of this matrix, but the determinant of this matrix is 1 times 1 times 1 times 10 is 10, which means that the determinant of A is negative 10. Okay, then I believe the easiest way to compute the determinant when n is big is to use these properties. Row reduction and the fact that if you have an upper diagonal matrix or a lower diagonal matrix or a diagonal matrix, then the determinant of that matrix is just the product of the elements in the main diagonal.